Greetings, Panthers. Dr. Augustine, how are you doing today, whenever you're listening to this? Today we're going to talk about a really important key concept in Chapter 3. And every chapter sort of has one or two or three sections that are sort of critical, and this is one of them for Chapter 3. This kind of unlocks the secret to actually a lot of the rest of general chemistry. This is a really important concept. We're going to talk about formula mass, which is not difficult at all, and then the mole concept for compounds, which is the really important part of this. So this covers Chapter 3.8, Intro, Formula Mass and Mole Concept. So we're going to explain what formula mass is. Depending on your book or other context, you might see it as the molar mass, or you might see it as molecular mass. I'm going to say molar mass and molecular mass kind of interchangeably with formula mass. I think Trudeau uses formula mass. And then we're also going to show how the formula mass can be used in calculations involving moles. And this is really a key idea. If you understand this is going to unlock a lot of the rest of general chemistry. So this is a key topic to sort of wrap your brain around. So one thing that's a little bit strange about Trudeau's book, I understand why he did it, but it's a little bit strange. He introduces the mole concept in Chapter 2 and then waits until the middle of Chapter 3 to introduce formula mass. And I do understand why he did it, but a lot of books have them done together. So you might want to refer back to Chapter 2 to understand where the idea behind the mole comes from. So if you remember back in Chapter 2, something like copper has a atomic mass of 63.5 AMUs. That's the mass of one copper atom, and the molar mass is 63.5 grams Cu for every 1 mole of copper. Okay, remember those are equivalent to one another. They're not equivalent in masses, but the number's the same. And why they come about is, if you recall, that the whole periodic table is based on the mass of carbon-12. So the entire periodic table was set up based on carbon-12 as your basis. One carbon-12 atom was defined to have a mass of 12 AMUs, 12.000 all the way to infinity AMUs. And if we had this magic number that equaled to 12.00 all the way to infinity grams of carbon-12, we called this, or defined this, to be 1 mole of carbon. 1 mole of carbon-12 specifically. And remember, that number is 6.022 times 10 to the 23 carbon-12 atoms, which is known as Avogadro's number. Okay, if we had created our own system, we would not have started with this number. This is experimentally determined. If we happen to have 12.000 grams of carbon-12, there are 6.022 times 10 to the 23rd carbon atoms. Okay, and we call this a mole. So this mole then is our dozen, just a way of grouping a large number of things. So in copper, 63.5 grams of copper is equal to, there are 6.022 times 10 to the 23rd copper atoms in 63 grams of copper. Why is copper 63.5 and carbon's only 12? Well, that's because a carbon atom weighs less than a copper atom. There's more neutrons and protons in the copper atom than there is in carbon, therefore it weighs more. Okay, and that turns out to be about 22 pennies worth of copper. Now, some of you might be saying, well, pennies are really zinc with a copper coating. Okay, fine. This is an illustration. Let's pretend these are pure copper. Okay? The reason why we use a mole is 12 grams is a reasonable amount that you can measure out in the lab. 63.5 is a reasonable amount that you can measure out in the lab. So these are quantities that are reasonable amounts. Well, of course, some things you can be found in their pure elemental form, copper or diamond or something like that, but there aren't a lot of things you can just dig up in the ground that are in their elemental form. Most of them you're going to find in the form of a compound. So let's start with an easy compound. Let's take something like water. So water, how much would a molecule of water weigh? One molecule of water is going to be the sum of the masses of the individual atoms. So 1.008 AMUs is the mass of hydrogen, and we have 2 hydrogen atoms, plus 16.00 AMUs times 1 oxygen atom. This is equal to 18.01 AMUs. That's the mass of one water molecule. If we had a single water molecule in atomic mass units, it would weigh 18.01 AMUs. Well, what if we had 6.022 times 10 to the 23rd water molecules? Remember, the number of grams is when we have the AMU number in grams, that's what happens when we have 6.022 times 10 to the 23rd. So likewise, when we have 18.01 grams of H2O, that is equal to 1 mole of H2O. Okay, so this would be called the formula mass or the molecular mass. This is the mass of a molecule, can now be determined just by summing up the individual atoms and their known molar mass, atomic or molar masses. Okay, so water is 18.101 grams per mole. If we were to measure that out, it turns out about a tablespoon of water contains approximately 1 mole of water molecules. It's approximately 18 grams. Don't use the tablespoon as your measurement. Use the 18.01 grams of water as your measurement. All right, so then that becomes a factor which I can use then to find out how many moles of some arbitrary amount of water I have. So let's pretend I have 36.5 grams of water. I can find out how many moles of water I have by multiplying times this conversion factor, 18.01 grams water for every 1 mole of water. Grams of water is going to cancel grams of water, and that is going to give me 2.03 moles of water. Checking sig figs, I've got 4 sig figs here, I've got 3 here, so this should have 3 sig figs. Okay, so it's a little more than 2 moles of water in 36 grams. So this calculation right here is one you are going to do so many times in chemistry, you should get lightning fast at doing this kind of calculation. Calculating grams into moles, grams of something into moles of whatever that something is. And the other thing I'm going to encourage you is to really carefully write these units down. Grams H2O, 1 mole H2O per grams of H2O. And the reason why you want to do that is there's going to be a lot of situations when we can switch from one species to another. So let's take this one more level deeper. If we have 18.01 grams of water, that means we have 6.022 times 10 to the 23rd water molecules. Okay, we already established that. How many hydrogen atoms do we have if we have 18.01 grams of water? Well, we have 6.022 times 10 to the 23rd water molecules, but for every 1 water molecule, there are 2 hydrogen atoms. So there's actually 2 moles of hydrogen atoms. There's 1 mole of oxygen atom, and there's 3 moles total. So if I said, what are the total number of atoms in water? It would be 6.022 times 10 to the 23rd times 3, because there's 3 atoms. All right, let me show this to you in a little more systematic way. Let's pretend then that we're starting with 18.01 grams of water. And I want to find out how many moles of water there are. So times 1 mole of water for every 18.01 grams of water. Grams of water cancels grams of water. Now I'm going to find out how many water molecules there are. 6.022 times 10 to the 23 H2O molecules for every 1 mole of water. Okay, and you're probably thinking at this point, well, we just said all this in words, so why are we writing out formulas for this? Because here's the next step that I want you to see. There are 2 hydrogen atoms in every 1 H2O molecule. That's that ratio that comes from the actual equation itself. So this last factor will tell us how many hydrogen atoms there are. And there's actually going to be 7.253 times 10 to the 24 hydrogen atoms in that same tablespoon. And if I had asked for what are the total number of atoms, then you would substitute into this position right here, you'd say 3 atoms for every 1 H2O molecule. That would go in and replace this whole thing. Okay, so What this concept, what this allows you to do then, is you can have any formula, any chemical formula, and you can see that there's a ratio of these atoms in there compared to the entire molecule. Now let me give you a weird example that I've given to my class many times, and that is pretend you have one of those cans of fruit cocktails. Okay, and let's pretend we have a couple of these guys, and I'm not going to draw too many of them, but let's say my fruit cocktails have one of those weird cherries, 1, 2, 3, 4, 5, say peaches or something. There's 5 in there. And then suppose I have 2 grapes in every container. And then let's pretend I've got, I don't know, 3 blueberries in every container. Okay, I know that cans of fruit cocktail do not have the exact same amount of everything, but let's pretend they had something like that. So what I've got then is 3 blueberries, 1 cherry, 5 pieces of peaches, and 2 grapes in every can. Okay, and suppose I had 10 cans of this in my closet. So if I had 10 cans of this in my closet, and I asked you, how many total blueberries do I have? You'd say, oh, that's easy. You have 30 total blueberries. And if I said, how many cherries do you have? You'd say, that's easy. You have 10 total cherries. If I said, how many peaches do you have? That's easy. You have 50. And how many grapes? I have 20. Okay, how did we know that so quickly? Because we know there's a ratio between these, which is 3 to 1 to 5 to 2. No matter what can I have, they're all in that same ratio. Well, that's what you have with the chemical formula. You have 2 hydrogens for every 1 oxygen. If you have something like, let's say HClO4, you have 4 oxygens, 1 chlorine, and 1 hydrogen. In every one of these molecules, you've got a 1 to 1 to 4 ratio. Just like in these cans, we've got a 3 to 1 to 5 to 2 ratio. So no matter how many cans I have, I can just multiply it by that ratio to find out how many there are, and they're always going to be in the same ratio. These are always going to be in the same ratio with one another. So that last step then allows you to convert from molecules into atoms, or specific atoms like hydrogen atoms. Okay, so we're going to take this and we're going to extend this analogy then to a specific sample. A student has a sample of 15.36 grams of magnesium. This is actually an acetate ion, magnesium acetate. And we're going to ask a bunch of different questions about it and show how to solve these. So first thing, we're going to stop the video, I'm going to clean this all up, and I'm going to zoom in on that.